Hello, good morning. Welcome to the second seminar of the Physics of Life South American Network, PoLSAN. I guess you all know by now the existence of this network, especially if you're attending this seminar. But in any case, I share there the announcement of the network with the QR code that gives you access to the website. And the idea is to organize activities, but organize them through 3 subnetworks, one on ecology and evolution, another one on from molecules to cells, another one on neurophysics. And you can join the network by subscribing to the mailing lists, to any of the mailing lists, all or one of them. So today we have the second seminar, as I already told you, which is on neurophysics. And we are very pleased to have Fernanda Matias from the Federal University of Alagoas here with us today. Fernanda did her undergraduate and a PhD thesis at the University of Pernambuco. And then the PhD, it was a sandwich PhD with the University of the Islas Baleares in Spain. She was a postdoc at the Laboratory of Cognitive Neuroscience in Paris-Saclay. And since 2014, she is an assistant professor at the Universidade Federal de Alagoas. And she's also part of the graduate program there as a professor. She's the vice chair of that program right now. And one of the, among her achievements, she received the L'Oréal UNESCO Prize, awarded in together with the Brazilian Academy of Sciences in 2022. And she's also very active in enlarging the participation of all sorts of people into physics. So she's part of the community to increase diversity in the practice of physics. And she's also involved in statistical physics within the Brazilian Physical Society. Today, Fernanda is going to give a talk titled Brain Dynamics, Data Analysis, and Numerical Simulation of Neuronal Circuits. And we welcome Fernanda very much. I will stop my sharing and let her share.
Hello, everybody. Thank you so much for the invitation, Silvina, Pablo, and for the initiative to beginning this excellent group.
And so let me add one thing that I always keep on forgetting, actually. We encourage everybody to ask questions, particularly students if they are present. And if you don't feel comfortable with English, please ask your questions, either raising your hand or writing it in the chat in the language that you are most comfortable with, and then someone will translate to English. Thank you.
Great.
Sorry, Amanda.
No, great. That's great. Can you see my presentation?
Yes.
Okay, I cannot see you anymore, so talk to me if something goes wrong. So I would do like, is it okay? So can I start? The idea is to talk about what I've been studying in the last 10 years, probably, in this part of physics applied to computational neuroscience, trying to model electrical activity of the brain and try to compare this activity from models to real brain signals from different experiments. So typically I like to start presentations with this GIF, in which something is changing every time the screen blank. Is something very big, but we take a while to realize what's going on. Since I cannot have all of your hands raised when you realize, if someone wants to put in the chat when realize what's changing, but otherwise I will tell you in a few seconds. But I like to say that after you realize, you cannot stop seeing it. And this is a kind of example that could be just a joke in family's dinner, but this can also be treated as science and trying to think about neuroimaging, about the universe, the brain as a machine that interprets reality, because the external stimulus is on the screen all the time, but sometimes we realize something and sometimes not. So for those of you that didn't see yet, there is this big bar in the picture, and every time it blinks, it changes. So it's something really big in the picture, but we take a while. So this is the moment that you say, oh, okay. It's a little bit difficult online, but the idea is try to understand how do neurons communicate with each other before we realize the movement of the bar, and after, what's changing inside our brain, even in a world that is doing the same thing since the beginning. So there is this difference in connectivity. If we think about functional and structural connectivity, our brain is more or less the same during these few minutes. So the structural, the anatomical connectivity is the same, but the patterns, the information, the electrical activity, the functional connectivity is changing when we change cognitive tasks and when we change cortical states. So we can approach these kind of questions in different ways. And the way I've been doing that is trying to compare neuronal data, doing data analysis, connectivity, information flow, entropy, complexity from different experiments with different animals, so monkeys, rats, human, using intracranial data, local field potential in animals, or even non-invasive techniques such as electroencephalogram, magnetoencephalogram. And then we have this time series of the electrical activity, and then we can analyze with different frameworks. And then we can go to models to trying to model the brain activity with dynamical equations, the differential equations, and trying to find biologically plausible ingredients that reproduce the same kind of real data that we find, or at least the same kind of phenomena. So we can looking for oscillation, synchronization. We can look for different levels of entropy, order, disorder, or the flux of information. And then we can come back to experiments and doing these, going back to model, trying to change inhibition, excitation, the model, trying to change things with real ingredients that come from brains analysis, and compared data and models and try to improve and understand a little bit what's underlying different phenomena. So today I will talk more about complexity. Perhaps in the end I can talk a little bit about more modeling, but I would like to to bring these ideas here because it's I've started this area with my collaborator, which is Osvaldo Rosso, an Argentinian. So I'm doing that with Luz Bavassi and Carly. We'll talk later, which is from Buenos Aires. So I think it's a nice thing to share here. And it's something that is kind of interesting to explain by hands. So if we look to disorder, if we look to entropy, we can have this very regular crystal or very regular pattern, and the entropy will be low, zero. And if we go to the other side, if we have a random pattern or this noisy thing, we should expect to measure entropy close to 1. We should measure this disorder being maximal. But then we have everything in the middle, so all this idea of complex systems, all these beautiful paints. And it would be nice to organize that in a way, in a framework, very organized as we have it for entropy. It would be nice to have it for complexity. We still don't have that, but if we can develop a math that goes in this direction, we would expect to have this kind of 2D planes in which we can find very low complexity, both for regular systems and random systems. But for these systems, like with intermediate entropy, we would have an increase in complexity. So can you see my mouse?
Yes.
Maybe,
okay.
Maybe you can do full screen as well?
No, we've tried and I couldn't,
Okay.
sorry.
It doesn't work.
So if we can define any kind of complexity and trying to see if we can use this idea for intermediate entropy, but high levels of complexity, we then could compare at least among similar paintings or similar patterns or temporal series. We can use this plane to have an idea of what's going on in the middle, in between the very regular and the very random. So I really like this idea, independent of what you are using to measure complexity or even entropy. You can use not the most common ones, but to have this plane that separate regular and random with low complexity and all these complex systems with high complexity. And then we could thinking about networks. So if we have very regular networks or random networks, it would be in the base of the plane. And then brains network or traffic network, all complex systems network would be something in the middle. And if we think about time series, if we have a very regular time series just increasing or a very random time series, we would have these in the zero entropy and zero complexity, or high entropy but zero complexity. And then we could compare different time series from the brain or from different dynamical systems. So this is what I've been doing so far, but for that we are using a symbolic information approach. So there are different ways to measure complexity or entropy in time series, and here I will talk about this bandit pump method, which is kind of easy to understand, easy to explain. And in the end, I will talk about we are using these ideas also to promote science for young girls, because it's an idea of histogram and statistical physics that we can understand with very basic principles. So I hope you can follow me. The idea is that if we have a time series here, no matter what's coming, what's generating this time series, we can looking for different symbols in this time series. So if we do a zoom here, the first 3 points here, we have this increase pattern. And then the second, third, and fourth point, we have again an increase pattern, which we are defining and counting here in this histogram. But then we can have different patterns as increase and then decrease. And we can come here and realize that this is this pattern, and we can count how many times the different patterns appear. So in the end here we have decrease, which is this last pattern here. And doing that, we can associate to each time series a PDF, probability distribution function, or an histogram with the frequency of all the symbols that we count in that time series. And then with this PDF, with this probability distribution function, when we can measure whatever index that we want to define. Typically, we can define channel entropy, which is the most well-established one. So we can come here and measure entropy as P log of P in this PDF, in this histogram. So we have just 6 numbers to sum, and there is something that we can do by hand for a few examples. And in fact, we will have these smaller values of entropy for a very regular thing. So if we have just one pattern here, so all the symbols are increasing, we have these maximum value, 1 for this pattern and 0 for the rest. So we have a small value of entropy. And if we have something very random here, we have a PDF that it's equiprobably, so all the symbols can appear with same frequency. So we have a high value of entropy. So we can use this idea to generate an histogram associated to whatever time series we want, and then to calculate whatever index, informational theory index that we define. So, for example, if we calculate here this entropy of this series and we find a number 0.432, and then we define complexity in a sense that I can explain in a while, and find a different number here, 0.341. Now we have a measure for this time series, and we can say that the disorder associated to this time series is something between 0 and 1 is this number. And the number associated to a measure of complexity that I define here is something in this number. So we can think and come to this plane, complexity, entropy, and mark where our time series is. So that's the idea, and how to compare to the plane of complexity that I was showing in the beginning. So if we have one time series and we calculate complexity and entropy and find the numbers here in the plane, we can come and compare now with a different time series, calculate complexity and entropy here, and see if these time series are similar, if one is more complex than the other, if one is coming to this region of very random situation or coming to this region of very regular situation. So the idea is to find measures that we can do that, trying to use this plane both to separate conditions, so to classify different conditions, but also to understand what's going on in that time series, how these measures are related to the parameters that we are choosing. So if we are choosing just 3 consecutive points, we have just these 6 symbols here. But if we choose more points, more consecutive points, then we have more possibilities of symbols. So we can look to the correlation of the neighbors' points in a larger set. So there are a lot of details that we can go on, but the idea is that we could think in how to separate here. And specifically in our case, we are using this statistical complexity measure based on the disequilibrium of Jensen channel, which means that we are comparing how different the entropy of the histogram of our time series is from the histogram of the equiprobably time series. So if we define PE as the probability distribution function of the equiprobably case, the random time series with similar values of all symbols, then we can define the complexity as the distance between this histogram that we have from the equiprobably, the one that everybody has the same probability. So defining this way, we can have this idea of 0 in the extremes if we normalize, and this is what we are going to use here, but there are a lot of different ways of defining complexity. So we can also use this approach to calculate different time scales. If we have 1 point every second, for example, we can say, okay, our phenomena is interesting every second, but what if we calculate not every second, but if we skip every point and the other, so every other point, we would have not the entire time series, but we would have something like this orange time series here that we just jump every odd point, for example. So we have a different time series, and now we can associate entropy and complexity as a function of these downsampling, as a function of this embedding time. So if we are not looking to every point. In neuroscience, typically we are looking EEG, MEG, in things around 1 millisecond, which is related to the time of a spike of the neuron, so 1 millisecond to do this all known to all activity. But then there are some phenomena that are more related to timescales that are larger, for example, 10 milliseconds, 100 milliseconds. And then we can compare what's going on to the complexity and the entropy of the time series as a function of our downsampling here. And sometimes this is interesting because we can say that, oh, okay, the time series is very random when we look every millisecond. So this time scale is not very important. But when we look to larger larger time scales, so around 10 milliseconds or 50 milliseconds, we start to walk in the complexity entropy plane to regions that are not very random and are more complex. So perhaps the information is being processed in this situation. So we can go for tau equal 3, then we can build these graphs here as entropy and complexity as a function of tau, and I will show this kind of graphs, these pictures for different brain signals. So with the methodology in mind, how can we apply that in real data? So we've started, for example, with this intracranial data from epileptic patients that have to go to surgery and remove parts of the brain. So they spend like a week at the hospital with these electrodes in their heads. And some of them volunteer to do cognitive tasks. And the doctors record the brain activity during that. And then this is an example of an intracranial site here. So it's this channel here in the brain of one of the 5 patients during this cognitive activity in which they see a white screen, a blank situation for 2 seconds. And then for other 2 seconds, they have a search visual task. They have to answer the color of the box according to the direction here and the star here. So what's the color of the box up after this star? So black here. What's the color of the block in the right side of this star here? So black again. But then we just compare blank situation with search situation, and the cognitive task consists in repeat that for hundreds of times, hundreds of blank trials intercalated with hundreds of search trials. And then we have the time series for different electrodes, 6, 7 channels in all these patients, and we can analyze with the symbolic approach. So this was all done for by Ícaro and Pedro, our students here in Maceió. And then we can calculate entropy and complexity as a function of tau. So every 1 millisecond, and then every 2 milliseconds, around 10. And we can realize that around 10 and 6 here, there is a difference when we compare these blank time series, these gray time series here from the search time series here. Then we can define a distance between entropy and complexity that is maximized for tau equals 6. So more or less here we can see that could be a good region to separate the 2 conditions in the plane. So in the complexity entropy plane, we can separate blank trials from visual search trials. And then we can do that for all electrodes for different values of tau. And we can see that many patients and many electrodes and many tau, so from tau equal 1 to 30, we can have these regions in which the separation is good. We can have these electrodes that don't care for the difference between blink or search. And we can have this tau very high that is not that interested to in the task, but then we can come here and found electrodes that are very active in separate the two things that are probably processing information about this cognitive task. And then we can ask, okay, we can look for these 2 seconds, the entire 2 seconds, but we can also look for different time windows here. We can look every 200 milliseconds here and do a slide window and see what's going on with entropy and complexity during the search, during the blank situation. And then we found that for different electrodes, we have different situations, but many of them are separating the 2 conditions in a moment here between 500 milliseconds and 1000 milliseconds. So we can try to start to interpret what's going on during the search or during the cognitive task. We can also find electrodes that are not separating any moment. Then we can go in a trial by trial basis. We can really look for each trial here and see if we can separate. And then there is this very beautiful electrode that for 120 trials, it separates very good. So we would have 100% of correctness if we look to the entire time series and ask, is this a blank screen or a search screen? And then we have electrodes that are very mixed. They are not separating the 2 conditions. We are electrodes that are something intermediate here. So we can start to try to understand, okay, these occipital electrodes in different patients, they have the same behavior, but then we have these electrodes here. We don't understand very well why these electrodes are doing the same. But then we can start to thinking about time scales using the time embedding the tau and also windows of time. So what's going on when we look to the arrow, to the direction of the arrow, or when we look to the color? What's going on when we answer something? And we can also thinking about new cognitive tasks. For example, if we first see on the screen the direction, so the arrow pointing for some direction, and then we look to the box, so we would have very precise time windows in which things are repeatedly, consistently happening. And then this could be easier to find differences in some regions that we are not finding here, for example. And there are this kind of thing for addition. So when patients are doing math, it's different if you show 2 plus 5 equals 7, so once in the screen, or if you show 2, then plus, then 5, then equal, then 7. So this is a kind of data that people are also doing experiments, and at some point we can using it with the same framework and start to understand differences of seeing these different tasks. So then we analyze a different cognitive task, this time with the group in Argentina, so Luz Bavasi, Maria Carla Navas. We received that grant of Móvil America, so I think we can use these to move to encouraging more people in this group to do this kind of internships. So Carla is here in Maceió for 4 months, and they did experiments of EEG in Buenos Aires, and she's here analyzing data. And we also put together in a collaboration with data from other groups. So we are analyzing this EEG during a go, no go task. So when people is looking for different images in the screen, and then if you see animal followed by other image of animal, you have to press a button. If we see animal and then a plant, you have to not push the button, so it's a no-go situation, and we analyze the entropy and complexity during all the trial. We are going to ignore these other two types of trial, ignore the novel, but then we have this data from 11 volunteers, and we expected that we should see difference between ghost trials and no ghost trials only after the second image. And we would like to know, for example, how long after the second image appears we can see differences in the complexity entropy plane when we have a go trial or no go trial. And for different channels in these electrodes here, we have different time in which this starts to appear, and we can see that the differences start in occipital and go to central areas after a while, and this is for one patient. And we can compare that with data from monkey that we have analyzed before, doing a similar go, no-go task. So there is a time in which we can see the difference in the intracranial and the LFP data from monkeys. And we can also see that in humans, and we can see that in the group average. And if we do just the ERPs, so the average of the electrical activity, we can just separate go and no-go trials at some point after the second image. And we are trying to show that with our method, there are some cases in which we can separate entropy and complexity before, like the distance in the plane is larger before, if we look just to the average, just to the ERPs. So our method is catching something in a time before that we would think that the decision was done about the kind of trial. So we use these to other applications in brain signals. Elena is analyzing sleep stage, so we can use it to differentiate different cortical states, not only cognitive tasks, but we can thinking about wake situations and sleep situations of REM, non-REM 2 and non-REM 3. So we have this open database from Canada with more than 100 patients and 1,700 electrodes for people during sleepy. And we can use this entropy and complexity to see if we can separate and in which regions we can separate the three conditions. So in fact, we can look for entropy and complexity for different values of tau, and we can see that a lot of values are good to separate. For example, 1 millisecond is not that good, but after 5 until 30, you can use it to separate. So this is giving information about the time scales that are more relevant to separate the time series. And then we can come to the complexity entropy plane and see that we can find specific order in wake, REM, and 2, and then 3 sleep stages. And we can go in this direction, which was observed with EEG, but not with intracranial before. And we are also comparing with models of whole brain, trying to say that as we walking from wake to different sleep stages, we always go in these directions to less random situation, I would say. And then we compared these results with grouping Recife with rats, and we have for rats and data from Buzak's group. Also, we have the same order here. We have awake, HEM, and non-HEM situation when we look to complexity entropy, so which is similar to human intracranial. And in these data from mice, we also look for the cortical layers. So we can also look the depth of the electrode in different layers of the cortex. And we have also realized that we have this maximization of complexity in layer 5, which was not reported before, and something interesting in the biological point of view. And we are also looking for more evidence of that. but it's something that we are happy to find this maximization of complexity here. And so I don't know about my time. If someone tell me, it would be nice.
If we want to have about, I don't know, 10 minutes talk or questions or
Okay.
something, maybe you should end in 15 minutes or
Okay,
10,
so
between 10 and
perfect.
15 minutes.
Okay, so perfect. I can talk about that. So the idea is talking about these complexity ideas of very regular and very random things. We decided to compare with criticality. So the idea of the critical brain is around for many years now, since the 90s. But for those who are not very familiar with, there is this idea that if our brain is acting close to a phase transition, close to a critical state, it would be nice, for example, that every neuron stimulates each other on average, like just one neuron. So every time a neuron fire in a layer, on average, this neuron will make just one other neuron to fire. So on average, every neuron stimulates one other. If we need many neurons firing to stimulate just one neuron, this would be a subcritical situation. And otherwise, if we have one neuron stimulate many neurons in the next step to fire, we would have a supercritical situation. So what does it mean? It means that if our brain, we need very high stimulus to stimulate neurons in the cortex, in the pathway to different cortical areas. If we have a cup of coffee here, we would need really to put our nose very close to this coffee to smell the coffee. Otherwise, we would not be possible to recognize this, the smell. In the other side, if we have a supercritical brain, if we smell coffee in the morning, we would remember this smelling all day. A lot of neurons would be firing because of these few molecules of coffee that we smell. So we hope that we have something in between, something that is critical and close to an intermediate situation that we can feel the coffee, the cup of the smell of the coffee, but not stay active all the time. And then this was shown in experiments for the first time, and evidence of that is that if the brain is close to a critical regime, we should found power laws with well-defined size. So both for the duration of spikes and for the size of how many neurons are spiking. So if we look to the activity of a slice of brain here in 2003, Bags and Plains shows that if we count the number of neurons spiking in bins, in times, interval times that we choose, between a moment of no activity and another moment of activity, we can count the time of the avalanche, and we can count the size of the avalanche, how many neurons spike here. In both situations, when we plot the probability of find an avalanche or spikes of neurons with a specific size or a specific duration, obeys a power law. So it means that there is no preferential size of these avalanches, such as in earthquakes. And these power laws are famous with Purbach since the 90s. And they show that they could be found in LFP of rats in brain slices. So it was the first experimental evidence that perhaps the brain is acting close to this situation of a power law, a critical regime. So in 2019, the group in Recife, they showed that anesthetized rats have this brain activity that goes close to a critical situation, in the sense that the activity fluctuates from very disorganized to very organized spikes. So you can have this situation for a while in which the rat just just anesthetize the rat and wait and see the activity, you can have this situation of very random here, and then it fluctuates for situations that are very synchronized here, but then almost of the time they are in something that is intermediate, and in these intermediate situations, they found a lot of signatures of criticality. So they show that the brain is moving around, the anesthetized brain of the rats are moving around situations close to these critical points with very specific power laws. And then this pop-ups in my mind as if you are going to something that is very regular for something that is very random, you are walking the complexity entropy plane, so perhaps we should expect that the complexity is maximized in something in between with intermediate values of entropy. So then we ask for data and start a collaboration with Nastra, which was here in Zoom before. So she analyzed the data with this framework of entropy and complexity, and also compared to the CV, this fluctuation parameters that they used before to say if the system was very ordered or very disordered or very ordered and synchronized. And then we analyze the same time series and calculate entropy and complexity in each point. And then we have that the entropy as a function of the CV is just a monotonical decrease function. So, I mean, when you are going to very organized situations, your entropy is going to very low values. And when we are very random here, your entropy is high, as we would expect. So the CV of intermediate values that have signature of complexity are somewhere here in the middle, and the entropy is somewhere here in the middle. But then when we look for complexity, then we have this complexity being maximized around the CVs of critical signatures. So we verified that with this framework, the complexity entropy plane, we can have states fluctuating in large regions of the plane, but in these regions in which the complexities are larger, we have exactly the other signatures of criticality, the power laws that we are looking for in the critical regime. So we did that for 7 rats. We have that for all the rats together, and we were very happy to find that results are consistent. And this was, as far as we know, the first observation of these maximization of complexity close to a critical state. And we compared with a model. So in a model that we really know where the phase transition is, a model that have this behavior, subcritical, critical to supercritical, with all these details, like a probabilistic cellular automata that has excited state, refractory state, and have been shown to have this branching ratio in 1. So if we know all the details of the model, we know where the phase transition is happening. And then we have here, we can compare the model with all the parameters and the CV of the 7 animals. And we have, again, this maximization of complexity in the model close to the transition point. And then the take-home message is, in fact, we can use this idea of disordered, synchronized states and critical states, and we expect that the critical states is higher here with complexity. So another group from planes, the one who observed for the first time these events in neurons with Tiago Ribeiro, which is a Brazilian that is there. They use this idea in 2 photo imaging data and calculate complexity and see that complexity was maximized in a temporal situation depending on the toll, the embedding of your downsampling, your time series that they call K here. So we are happy to see that this is being investigated in other experiments. I have with this, I would stop the complexity part. I would have something to talk about models, but I'm not sure if I should go on here or we can just stop and ask questions. So I think I'm going to the end. And I would like to thank you all my students, all my collaborators, especially Professor Osvaldo, and all these initiatives for human and diversity in science. So this Brazilian Society of Physics has this commission for diversity, which is very important now. And then just to advertise, we have 20 students from ensino médio, I don't know, before entering the university, they are learning these techniques of doing histograms in a very funny way. And they are doing this Iniciação Científica Júnior, trying to analyze temporal series in a big project from CNPq to motivate girls in science. So this is a 3-year project. We have just started this year. I hope I can have very great news for the girls in few months. So that's all.
Great. Thank you. Thank you very much, Fernanda. And also thank you for for leaving some space for questions. So we open the floor for questions. Please raise your hand or write. You can, I don't know, you're still sharing. I don't know if you want to keep on sharing.
Yes.
You're sharing my face, basically.
Sorry, I can share both. Let me try to put
that's it. If you keep that one, it's fine.
Perhaps something like that.
That's fine. That's fine.
If someone asks.
Yeah. So Robinson Jose raised his hand. You have to unmute if you want to ask.
Can I see him? No.
No, I don't know. Maybe it was a mistake. So let me see if in the chat there are other questions.
If I can start with one.
Yeah, you can start, Pablo, please.
Sure.
Hi, Fernanda. Thank you very much. This is all very nice. I have a question regarding other systems where this technique can be used and similar ideas about biological systems living near criticality. So there is this idea floating around that tissues, they have a rigidity. So the rigidity of the tissues is around some critical rigidity transition. So the tissue could be really floppy, not rigid, or it could be a very stiff tissue. And they measured the rigidity of these tissues, and their rigidity is around some critical rigidity transition. So the argument there is that biologically, this is interesting for the system. So it would be evolutionary advantages because sometimes your tissue might need to be stiff, and sometimes your tissue might need to be rigid. So living around the critical rigidity transition makes your life easier because you can switch between both more or less easily. Is this kind of idea also going on about the critical transition in neurons?
Nice to know about rigidity. I would be happy if someone can use these ideas. I would have to understand better what you are measuring, if something in time or space, but of course, the methodology would be the same. And in the philosophical point of view, I've seen a lot of discussion in neuroscience that if the brain is critical, why is it going on? Is just an epiphenomena or is really evolutionary useful? And since I'm coming from this school, I mean, sounds great. No, you are there close. If you need, you go for this very non-localized situation, and then you call everybody. So you have this long-range interaction. So I think it makes sense, but perhaps I'm I'm just very influenced of all these ideas. But in this point would be similar. So if the teacher needs to activate, so it's better to be close to that. But who comes first? I don't know.
That's nice. Thank you.
Hi. Can you hear me?
Hello.
Yes, yes.
Okay. First of all, thanks a lot for the great presentation. Well, I'm Robson from Federal University of Paraná in Curitiba. In our group, we use recurrence microstate to define different kinds of entropy, which we call microstate entropy. So my question is, have you ever used recurrence plot to analyze your time series?
Not me. I know different works, not in neuroscience, perhaps in environment science, that use different many different entropies idea. I don't know if I know which one you are talking about, but in principle, you can use the same idea for whatever entropy you want to define or count in states. So if you have a way to define your probabilities, so you have a number for entropy, then you can have a number for complexity, or you cannot use not just entropy and complexity, but different entropies in the issues in the plane. It's possible, but I'm not aware of a specific paper with.
Okay, thanks.
Jaderson.
Hi, can you hear me well?
Yes.
Yes. Hello, Jada.
Oh, hello, Fernanda. Thank you for the very nice talk. And well, I've seen your talk, I think, in something similar in Encontro de Física e Estatística, but now I think it's improved and very nice. My question is there something on the direction of using criticality or these complexity measurements as a biomarker for brain diseases or things like that? Because like if you need to be in a critical state to be, say, healthy or in a complex place in the plane, so if you are, let's say, with some disease, maybe the complexity is lower, the critical exponents are different. Is there something on this direction already developed?
We should have organized the question. So here is there is this work in progress from Graça, which is doing a PhD, and I've just received a grant from Ciência Pioneira to do this kind of analysis with people with dementia and try to find biomarkers for Alzheimer, which would be really nice. But in principle, could be just try to characterize the health brain and separate for different ages. And then if we have this map of complexity and entropy for the health brain, we can use different groups with different disease and see if we can find the differences and which biomarker would be. But yes, it's something very appealing, it would be nice to have clear separation in the plane. Perhaps this is not what's going on, but with these MAGI data, for example, perhaps it's easier than with EEG. And then now we start to have this open data site with MAGI. So this is what we're trying, but still don't have results.
Thank you. Alonso.
Sorry. Just to complement, 2 days ago, someone sent me a paper. The title is Amyloid Pathology Reduced Dynamic Range. Exactly that. How the Alzheimer and the dynamic range are related, and this leads to something like a criticality.
Oh, nice.
Then
Send to me,
I
please.
just
It's from Palva's group? Palva and Palva? Probably.
No, first author is Mary Ann Go, and last author is Simon R. Schultz.
Okay.
Then
Nice.
just coming 2 days ago.
Maybe you can put the link in the chat. If you can put the link in the chat, that would help. I'm sorry, I think it was Alfonso that had raised his hand. And Was it?
Yeah, it was me.
Alonso,
Alonso.
Not Alonso.
Yeah. Well, first of all, thank you for the talk. It was very informative. And my question was maybe a dumb one because I didn't notice if you referenced it in the first slides, the paper in which you use the symbolic information to measure entropy and complexity, because in a very coincidentally in a very coincidental manner, I'm also trying to study complexity in models of the brain, specifically models of Couplet oscillators. And we measure the synchronization and desynchronized states by, it's actually anomaly detection. But measuring anomaly detection in this plane of complexity versus entropy might be actually a very good idea to implement. So could you please reference me to the paper where you used the method to maybe use it too?
Yes. No, yes, I know I can put here. I have the chat.
You're still sharing, so you can go back to your presentation if you
Yes,
want.
yes, it's just because I
Fernanda.
probably have mine here, but the first one from MPR, Martin, Platino, and Rosso probably is not right here. But for sure, if you
But
go
if you
to
give
our
yours and you
yes,
take your
yes,
pesticides, then it's okay, I would
yes.
say.
Okay, this DAPAS is a physical review E from last year. And then in the methodology part, you have these the specific papers also for the symbolic approach, which is bandit pump, and for the complexity, statistical complexity in the way we use, that's from Martin. So I think that there are all the references, and there is also idea from another Argentinian, Hopes Luis, like a previous paper, so it's also cited there.
Thank you very much.
Clara.
Hello, can y'all hear me?
Yes.
Okay, my main question was, I've done studies with like caffeine in the past, specifically with flies, not with rats, but I was wondering if there's any evidence or potentiality that caffeine could affect the complexity or entropy in the brain, if you think that would be something that's possible.
That's amazing. I've just seen, I think last week, something about caffeine and criticality. And I didn't see anything using complexity, but probably the, the same kind of data that they found criticality changing with caffeine, and I think it was humans, but I would have to look for. And yes, but I'm not aware of a paper using complexity and entropy in this way and caffeine, so it would be nice to see.
Okay, thank you.
You're welcome.
Are there any other questions? I have a question. I have actually two questions. One is, I noticed that you plot these theoretical curves, no? And in between you put the points. And sometimes the points are closer to one of the curves and some other times closer to the other. Does that give you some information of what's going on?
Yes,
What
perhaps
does it
here
mean?
just okay.
What does it mean?
Okay, first of all, these curves, black curves as maximum complexity and minimum complexity for each value of entropy, they are this way because of the definition of complexity that we are using. So since we are using complexity like a function of entropies, when we choose the number of consecutive points that we have, we can find this curve here, this maximum and minimum. So it's not possible for d equals 6, for example, 6 consecutive points, to find a value of complexity here and the entropy here with these two formulas, okay? So if we change the complexity way of using, we would change the boundaries. And if we change the parameters, we also change the boundaries. Okay, first thing. The second thing is that there are studies with chaotic equations, so dynamical systems that we know the dynamics, and as we add them, so chaotic behaviors have these values very high here, and as you add noise, you go to this direction of random. So there is this explanation that you can also use this plane to separate chaotic from stochastic behavior. But of course, if you are compare things that are comparable, I mean, if you start with a chaotic system and start to add noise, then you see clearly how the system goes through the random. In other cases, you cannot just say, oh, this is totally random or totally chaotic, but you can use to have an idea that in the top part, you are more chaotic, more deterministic.
Okay. And then the question that I had also was, you know that when you get these EEG records, you can also try to tell apart the contributions of individual neurons. There is a processing that you can do on that. I know, I mean, I've heard talks about that. Basically, Rodrigo Quiroga, he does that to identify the famous neuron of Jennifer Aniston.
Okay.
I was wondering, when you have this problem that things overlapped and you couldn't tell, I mean, different regions that didn't have a clear separation in that plot. If you never try to individualize the contribution of different neurons or something, like clean the data, and maybe that would tell apart those regions.
Okay. We did that for rats, like not that data from Rodrigo, that it's intracranial in humans, and you can have both local field potential and each neuron. I don't have yet, perhaps, if he wants to share. But for rats, we have like these results in Recife. We also compare when we look just to firing rates, as the time series of firing rates and the time series of local field potential. The thing is that if we look just one neuron as the Jennifer Aniston, it's very hard to do the symbolic approach, because then you have a lot of silence, then one spike or another. So we need this firing rate of lots of neurons, at least hundreds of neurons, to have an average in the signal. So in this paper of criticality, we are using Nastar analyzed firing rate. So these curves here is, so we can look to one neuron each time, but then we cannot do the symbolic thing, and we don't have this sufficient statistical. But here, this is firing rate. So we have all these raster plots, each one is one neuron. So we did like, okay, if we have not all neurons, but just part of it. But then when we go to very small numbers of neurons, we lost the power of the method. So it's something between. And if we look to the same data, not to the firing rate, but the LFP, it's not a direct relation. So these other results here are with LFP, and then you can look to layers, but you cannot directly compare with the firing rate. So we are still trying to understand the relation between this local field potential and these neuron firing rates that we can find from the same electrode, just sampling different.
Okay, thank you.
Can I have a quick question? Vitor first.
Okay, Vitor raised his hand, then Marcus, and
Fernanda.
then we have to wrap up.
Very, very nice talk, very inspiring talk. Congratulations. Just a general question, more in terms of how we try to somehow identify and distinguish between like healthy brains and non-healthy brains. For instance, you said about your approach to look at Alzheimer, and of course you have all this epilepsy and so many different behaviors that has like, they always expect to find like clear signatures on that. So could you comment on how far they are reaching in terms of practical terms? I mean, because it's one thing is how robust are the signatures, or are they too close that you can't usually you can use to do any kind of a clinical inference on things that would be useful. Could you comment on that?
Okay, first, I'm a physicist, not a neuroscientist, so I hope I'm not going very wrong, but the impression that I have is that in neuroscience community, in this neuroimage community, everybody do frequency approach, so Fourier transform. So the healthy brain is well established for many different cognitive tasks. If you have alpha oscillation, beta oscillation, so this is a way to looking for biomarkers, because then if you have now a group with a disease, for example, I'm here. Okay, just stop a little bit.
You're okay. You're okay.
So when you have a group of kids with attention deficit, for example, so they know that there is this decrease in alpha in specific moments. So this is biomarkers that people are using for neurofeedback and are using a red, even without understand completely, they are using to treatment and put kids to playing games and trying to just increase or decrease alpha somehow. The thing is that, okay, since we have these all other statistical physics measures, we could have, like, in a big effort in the world to characterize everything that we have for the healthy brain and then trying to look for biomarkers. But I think it's not going to be one group with experiments with 20 healthy people and 20 Alzheimer's. So that's what we are trying to start with, this big data set with Maggie, with people from 10 to 90 years. Then, of course, I could help with this complexity and entropy, but different groups would help with different statistical measures. And I think this would be something that needs these big efforts to really have this map of what is healthy, because there is a lot of variability, and then start to looking for biomarkers and machine learning, and then you can use you can use complexity as a feature for machine learning, and then we start to have increasing performance. It would be nice to find the biomarker that is exactly in the hippocampus and is that. But to be realistic, I think it's something that needs to be built in this open science community.
Is there room for, let me kick in. I'm sorry, Marcos, I'll give you the floor in a second. Do you think there is room to generate data in our region and advance with looking at something specific? I mean, so, geographical region, I mean.
This Ciência Pioneira project is to analyze Maggie, and I realized that in Brazil we don't have. I'm not sure in Argentina, but it's a very expensive machine that hospitals don't want because it's more for research than for really the treatment. But after we have these maps with Maggie, it would be really nice to compare to EEG. So if you already know where is the biomarker, so we can compare to EEG, which is much cheaper, and we have a lot in our region, so we could do this approach. And also this intracranial data. So there is these big groups in Europe and the US, and every time I write grants, I say, we need to have people here in South America knowing how to analyze this data, because at some point we can do this in Brazil, in Argentina, but I don't know how long it's going to take to really these hospital groups are interested in have this together with the university. It's political.
So, Marcus.
Okay, thank you. Thank you, Fernanda. Very nice talk. My question is the following. These calculations that you do on complexity and entropy, they are based on a single time series. You do it for each time series. And most people several people are interested in correlations between the time series so that they can build some sort of brain network. When you do it for each time series, are you missing something about this big picture? How do you connect the local behavior with the global behavior?
Okay, great question. Historically, I came from correlation and Granger causality analysis. So this is the everybody wants to know the information flow. But then we had a lot of different problems of how you are measuring and deciding of thresholds. I think I didn't implement yet, but I have already talked with Fernando Borges that is here and asked the question. Probably there are many ways of using this idea, comparing two and using the symbols of two. So if you do correlation using the chance of appears a symbol in one and the other, then you define your new PDF, and then you can define these for the correlation. But I'm not aware of a red methodology that is doing that. I think they have this with mutual information, and probably similarly we could adapt it to this complexity or bandit pump specifically. And yes, it would be nice to have. And
okay, thank you.
You're welcome.
So thank you. I think there are no more questions and we are about to finish. So maybe you can stop sharing, Fernanda. And we thank you again and thank all of you who have participated in this very lively presentation.
Yes, thank you so much for the questions.
And we hope to have the next meeting in a month. It will be announced soon.
Okay.
Thank you. Bye-bye.
Thank you.
Bye.